On December 21st, 2015, the company SpaceX successfully launched and landed a reusable rocket known as Falcon 9 on land. On April 8th, 2016, SpaceX recreated this launch and landing, this time having the rocket complete its flight on water rather than land. The Falcon 9 technology and research is predicted to replace the old school way of landing a rocket from space. The old school way was pretty simple as it included falling, crashing, and burning. The main benefit of a reusable rocket is that it will save a lot of money. This is because a new rocket is not needed to be built from scratch. Without a reusable rocket, it costs on average more than $20,000 for every kilogram of cargo launched into orbit. That means it would take $5,000 to send a single quarter to space. A reusable rocket also will cut back on the amount of time between launches. Rebuilding a rocket can take anywhere between 18 months to 5 years. Therefore, a reusable rocket will allow us to cut that time in half, also giving us the opportunity to send more vehicles into space with the saved money and time. So it makes sense that these two successful landings are a big deal in the industry of spaceflight. But if this was such a great advancement, why was it not completed earlier? In order for a rocket to land without crashing or burning, it must combat its main enemy, torque. Torque is a measurement of a force that has the ability to make an object rotate about an axis. It can also change the object's angular velocity. Factors that affect torque include the perpendicular force applied and the distance between the force and the axis, also known as the radius. In mathematical terms, it can be written as tau equals F times R. We can also use Newton's second law to describe torque. It is very similar to Newton's second law with forces, but this time we'll have net torque equals moment of inertia times angular acceleration. Moment of inertia is the sum of all masses times the radiuses squared. Then, if the point of application of a force is farther away from the center of mass, then the moment of inertia is greater. The moment of inertia changes with the shape of an object, but the most general form is a point mass, which is mass times radius squared. It is possible to calculate the moment of inertia for an object by taking the integral of the radius squared with respect to the object's sum of masses. Like forces, torque has the ability to do work. Torque and work have a linear relationship. The more torque you apply, the more work is being done. Work is defined as a change in energy. Therefore, when work is being done, it can be assumed the energy of the system is changing. When a rocket falls back down to Earth, it must combat high temperatures, velocities, and forces. In order for re-entry to take place, the rocket must first fall back through the atmosphere. The two main forces come from the friction of the air molecules against the exterior of the ship and the force of gravity. And while it may just be air molecules, it can often act as a solid concrete wall that the rocket must pass through. As the rocket begins to fall through the atmosphere at a speed of 10 kilometers per second, the air molecules hit the exterior of the ship, therefore causing a force of friction. The heat given off by this friction will increase the temperatures around the entire ship. Therefore, the ship will be required to have many layers of heat-resistant material so that the ship does not burn up in re-entry. These many layers also affect the force of gravity as the mass is then increased. Our example, the Falcon 9, weighs 529,084 kilograms without cargo. Because this rocket has such a great mass, the force of gravity acting upon it will also be great. The force of gravity acting upon an object can be calculated using the equation force equals mass times gravitational field strength. Gravitational field strength is always constant and will equal 9.8 meters per second squared. Additionally, there is a drag force acting upon the rocket that points in the opposite direction of the force of gravity. As an object descends through the atmosphere and falls back to Earth, it has a tendency to begin rotating violently. This rotation is caused by the torque generated by the drag, frictional, and gravitational forces acting upon the rocket. Rockets are unmanned when they re-enter the atmosphere, so no measures are taken to prevent the violent rotation. In capsules that carry astronauts, such as the Soyuz, preventative measures are taken to stop rotating. There are sensors all over the capsule that can detect when a torque is being applied. On the exterior of the ship are thrusters that will make adjustments according to the torques applied. The forces applied by the thrusters will counteract the forces that are causing the torque. SpaceX applied this same concept to the Falcon 9. In addition to thrusters, SpaceX has added what is considered the rocket's steering wheel. Upon re-entry, honeycomb-shaped fins will be deployed from the rocket. These fins will act as a balance and can adjust the rocket's moment of inertia by decreasing or increasing, which will counteract torque. As stated previously, the torque is dependent upon the radius. These fins will increase or decrease the radius between the forces applied and the center of mass of the rocket, therefore increasing or decreasing torque accordingly. These fins can act as a parachute and slow down the rocket, can change the torque accordingly, and also steer the rocket into a certain direction.